Just to confirm, please, if you can hear me clearly and you can see my whiteboard, just type yes in the chat room before I go on. If you can hear me clearly and you can see the whiteboard, just put yes so that I know that I'm not speaking to myself. Okay, great. Thank you, Akiode Yusuf. So welcome to the second tutorial session for MEG 805 based on chapter 2, tensor algebra. For those of us that missed the interactive session, just to explain to you why we've just been having tutorial sessions, we've not been having proper lectures yet. Continuum mechanics starts from the topic kinematics, but there's a language of continuum mechanics that has to do with vectors and tensors. And like I said in that session, I recognize that we are all coming from different institutions and there might be some knowledge gaps. So chapters 1 to 3 of the recommended textbook is what covers the knowledge gap before we can start the real topics that we need to cover for continuum mechanics. And that is why I directed you to the webpage, the materials, so that you can do a self-study of the review of vectors and tensors and take a self-test so that you can be prepared for the time that we'll start lectures proper. You already have a schedule, and in the schedule, anywhere you see R, it means review. It means a self-paced learning. Anywhere you see L, that is when the proper lectures will start. And you will see that where we have chapters 4, 5, and 6, you have L's, not R's. So we are still in the review of the language of continuum mechanics. There is no way we can do continuum mechanics if you don't know what is going on in chapters 1, chapters 2, and chapters 3. So the purpose of today's tutorial session is just to prepare you to take your self-test after you have gone through the materials. I don't expect that anyone will be in this tutorial session and have not gone through chapters 2, the lecture notes, the book itself, the chapter, and also the recorded videos on the website. So if you haven't done that, you might have a lot of questions, but what we do today, we'll spend about 1 hour, 15 minutes to take some of the questions so that you can go back and use the knowledge of today's tutorials to practice more. Then on Wednesday, we come back again at 9 a.m. To do another level of tutorials for about 1.5 hours, from 9 a.m. to around 10:30. Is that good for us? We should just spend about 1 hour, 15 minutes, 1.5 hours today. Wednesday again, another 1.5 hours, because I just feel that it might be too much for you to take for 2 hours at a stretch. Is that good? Can I go on? Because we are not very many in today's class, we are just about 9. You will also have the opportunity to unmute, because since we are not many, we are just very few. So I think we can control that. But if you know you are in a noisy environment, please just put your questions in the chat room. But if you feel that your question is something that you need to ask verbally, you just raise your hands and I'll ask the admin to unmute you, okay? So let's go on. So in chapter 2, we're looking, that's when we start looking at what actually is a tensor, different types of tensors, the characteristics of tensors. We looked at tensor invariants, and the very, very important foundation of chapter 2 is to recognize what a tensor is. A tensor is a linear transformation of a vector that produces another vector. So for example, if I have a tensor T, if it operates on a vector, it gives birth to another vector. But the most important thing that you need to know is that T is a linear transformation. Why is this important? It is not all transformations of a vector to another vector that is a tensor. For it to be a tensor, it has to be a linear transformation. How do you recognize a linear transformation? Number one, you recognize it by how it operates on the sum of two vectors. So the first thing is that if it operates on the sum of, for example, u plus v, it should give you TUTV. That's number one. Number two, when it operates on the weighted sum of several vectors, it should give you this kind of product. Of, let me just say, if it operates on the weighted sum of several vectors. So if, for example, T operates on the weighted sum, let's say for this case, weighted sum of two vectors, it should give you T alpha U plus T beta B. And this should also be the same as writing this. So there are two things contained in this number two. You will see that number one, the tensor is operating on the scalar multiple of a vector. This is another scalar multiple of another vector. So this is the third condition. When it operates on the scalar multiple of vectors, it gives you this. The most important of these three that captures everything here is this second one. So if you have a transformation of a vector to another vector, but it doesn't produce this kind of results, that is, if it is not a linear transformation, that operation is not a tensor. Fisayo, okay, let me see. Don't worry, we take attendance multiple times. So it's not only at the beginning of the lecture, because we know some people might have internet, fluctuation. So we take attendance like 4 times at the start of the lecture, the middle of the lecture, towards the end of the lecture, okay? So even if you switch devices, it's still fine. So on this foundation, we are now going to proceed to take some of the questions at the end of that chapter, which is the main reason why we are here today. The main reason is for me to go through those solutions at the end of the chapter. And if there's any that you don't understand, you might need to refer back to the notes themselves. So if you have not gone through the material, today's tutorial class might not really be of benefit to you. You should have done that before coming. So number one, if they ask you what is a tensor is a linear transformation of a vector that produces another vector. That is just what a tensor is. It is not every transformation of a vector to another vector that is a tensor. The transformation has to be linear. So I'm going to start from a very, very simple exercise in the solved problems, which is 2.1. We'll start from the simple ones and we move closer and closer to the ones that are more challenging. So let me just take this off. Then we move on. So 2.1. I want to believe we all have chapter 2 opened. And if you go to the end, which is example, so I'll just be calling the questions. I can't write it on the board. We'll be taking too much space. I'll just be reading the question out. So 2.1 says, show that for any tensor T, T operating on this basis vector EI. Remember that your EIs are also normal bases from chapter 1. And we now have a diode on EI. This is the same as EI, a diode of EI, and the transpose of T operating on EI. Now, for the purpose of the fact that I'm writing on a whiteboard and I'm not typing, you will notice that your tensors are in bold capital letters. So if you are looking at the notes, I just want to tell you the difference between for you to recognize the tensor, recognize the vector, and recognize the scalar. So capitals, when you see me write anything in capitals, that will be a tensor. If you see me write in small letters and I put a bar at the top, then that will be a vector. If I just write ordinarily, it's not in caps and there's no bar, that will be a scalar for the purpose of the whiteboard. But if you are looking at your notes, you will see that the tensor is caps and in bold. The vector is in small letters and in bold. And the scalars are in italics and not in bold. So when you are reading through the notes, that is how you can recognize from what is being typed, which is a scalar, which is a vector, which is a tensor. So how do we proceed with this? The first thing I want you to all recognize is that when a tensor operates on a vector, it gives birth to a vector. So what you have inside this these braces, or should I say brackets, this is a vector. You must be able to recognize that because a tensor is operating on a vector. And when a tensor operates on a vector, it gives you a vector. So that is a vector. When you have the dyad of a vector and a vector, when you have a dyad of a vector and a vector, it gives you a tensor. So another skill you must be able to recognize is to recognize the operations. To recognize which particular operation gives you vectors, which particular operations gives you tensors, and which particular operations gives you scalars. Because there are some rules. There are rules that apply to scalars, but cannot be applied to vectors. Some that apply to vectors that you cannot do for tensors. And examples we saw in chapter 1. For example, in chapter 1, you can only perform a normal multiplication for vectors. For example, I can say 2 times 1. 2 is a scalar. I mean for scalars. 2 is a scalar, 1 is a scalar. So I just have that multiplication. But if I put 2 vectors together, let's say I have A and B, and I say I want to find the products of these 2 vectors, the question you should ask is that what kind of product? Because you can have different types of products. You can have a scalar product. You can have a vector product because a scalar product gives you a scalar. Then you can have a tensor product, which produces for you a tensor. So you can see that for scalars, these 3 operations you don't have when you are looking at scalars. You just have your normal multiplication. So those are the kind of things that you must recognize when you are going through your vector and tensor algebra before we come to continuum mechanics. Now, if you look at the right-hand side, of course, you recognize that this is a vector. You recognize that the transpose of a tensor gives you a tensor. The transpose of a tensor gives you a tensor. So T transpose is a tensor operating on a vector. So what you have also in this bracket is a vector. And of course, when you have the dyad of those 2 vectors, you have a tensor. The only way you can actually show what is going on with a tensor is the way it operates on a vector. So for this particular proof in 2.1, that is why you would see, if you are looking at your notes, that we have to consider an arbitrary vector. So I have to operate this tensor. What I have written here is a tensor. So I have to operate the tensor on a vector and see whether what I have on the left-hand side and what I have on the right-hand side will produce the same results. If they produce the same results, then what it means is that what I have here is correct. So let's start from the left-hand side. This is what I have on the left-hand side, and it is a tensor. Of course, you recognize that because you see that dyad product of a vector and a vector. Now, let's assume that it operates on an arbitrary vector V. What does it give me? From chapters one, I'll refer you back to that. And that is why chapter 1, you must understand what is going on there before you come to chapter 2. You remember in chapter 1, we introduced the dyad product where we had something like this. And if you recall, when this dyad operates on a vector, it gives you a scalar product of the two vectors. That comes from chapter 1. Another hint that I will give you concerning tensor algebra is what we call pattern recognition. You must be able to see an operation and be able to recognize the pattern of the results. If you look at what I just wrote now, you will see that B, which is closer to the other side of the bracket, is what you dot with what is outside the bracket. And what is on the left side of the dyad comes out of the bracket. So if you recognize that pattern, you can apply that same pattern to the example we are looking at. So this will give us TEI, which is a vector, and you now have your EI dot V. Because EI dot V is a scalar, I can switch that around without making any serious error. It is only when you have a scalar product that you can move the vectors and switch the vectors. But if it's a vector if it's a cross product, you cannot switch the vectors. So it means for the answer I have here, I can rewrite this as this. Also from chapters 1, you will see that these results will give me CEI, VI. And in the bold notation, this is the same as writing TV. Any questions at this point? We are only looking at the left-hand side now. I'm now going to go to the right-hand side, and we will need to get the same output for us to say that the left-hand side indeed is equal to the right-hand side. Any questions before we move on to the right-hand side? Bolaji Idowu, you might need to talk to your class so that they can put you through how to open it. And if you need it almost immediately, you can ask maybe anyone in the class to post it on the WhatsApp group, okay, so that you can easily access it until you're able to sort out opening it on the web page, because it can be downloaded. Chapters 2 and the materials there can be downloaded. So any questions? I just want to encourage you to quickly respond to me, because when time is going, it means that it shortens the number of questions we can deal with. except you are writing. So please let me know what is just going on. You know, it's a virtual class, I can't see you. So let me know what's going on. So I've just written the operation on an arbitrary tensor, on an arbitrary vector for the left-hand side. And you can see what I got. So we are going to do the same to the right-hand side. For my own notation, because I am typing, I don't write my tensor with a bar so that nobody will be confused. I explained this when I started the class. When you are typing, like you see in your notes, your tensors are written in capital letters and bold. But when I'm writing on the board, I just write it in caps. So when you see me write anything in capital letters, just know it's a tensor. I hope that is clear, Bolaji. So I'm going to take off all this from the board. So now let's go to the right-hand side and let that tensor operate on a vector. So let me take this off. So on the right-hand side, we have EI, the dyad product operating on this vector, transpose of T, EI. Okay. So that's what we have at this other side. Now we'll know that when we have a transpose, if I move it around the dyad, or let me just write it in this form. T in index notation can be written as T alpha beta, E alpha, E beta. That's in index notation. T transpose, all you just need to do is to swap the basis vector on the dyad. So this is the same as writing the transpose in index notation. Just swap the basis vectors, and that's the transpose. Okay. So when we now want to have this operate on our arbitrary vector V, what do we have? So what we will have is EI, dyad of T transpose EI, operating on V. And using the dyad product operation on the vector that we saw in the previous, on the board previously, this is the same as saying EI transpose EI V. And of course, from chapter 1, this is the same as writing EI transpose VI. That's the same as writing that. And once you move your transpose, from its position here in front of the first EI, then you have transposed again. What I'm saying is that if I move this T transpose here, what I've done is that I have done a transpose of that transpose. I will explain myself. What I'm saying is that EI, which you will see in chapters 2, TTEI, is the same as saying TT, that's transpose of T, transposed again, EI, EI. So once you move this to the other side of the diode. What you have done is that you have transposed that tensor again. And the transpose of the transpose is the tensor itself. So this is the same as writing TEI, diode EI. So without even going through the proof, you will see that that is what we already have here. So it's like I'm writing in this case now, this would be TEI VI. And that's the same as saying TVI EI, which is the same as saying TV. So we'll see from here that the left-hand side and the right-hand side gives us the same thing. And what I've done here is I've used two methods. This is the first method for the right-hand side of showing that. And this is the second method on the right-hand side that shows that. Of course, the second method is shorter, and the second method can also be used for your pattern recognition. Pattern recognition in the sense that when you move a particular tensor on the other side of the diode from its initial position of where it is on the diode to another position, you have transposed that tensor. So this second method is what you continually make use of as you go through some of the exercises in chapter 2. Any questions? Any questions? I want to move to 2.4. Should I go ahead? Okay, Polaji, thank you. Okay, good. Let's see. Okay, I got 3 responses here. Okay, good. So let's move to 2.4. So 2.4 says, show that the transformation, so there are 2 questions there. Show that the transformation TV is equal to A dot V E1. Okay, show that the transformation ATV is equal to A dot VE1. And the second one, so this is the first question. And the second one, which is TV, which is equal to A cross V, are tensor transformations. So that question is just telling us to prove that these 2 transformations are linear transformations. We have to prove that these 2 transformations are linear transformations. So let's look at the first one. Remember that the first one is just operating on V. But for you to see, to actually see that a particular transformation is linear, you have to operate on the weighted sum of 2 vectors. When you operate it on the weighted sum of 2 vectors and you look at the output and you see that the output actually transforms linearly, then you can now say, okay, this is actually a tensor transformation. So instead of having V, we are going to replace our V. Instead of just having V, we are going to replace our V with the weighted sum of 2 vectors. And the weighted sum of 2 vectors chosen, as you can see in the note, is alpha U plus beta V. So what it means that anywhere you see V in the question, replace it with this and see how it transforms. Replace it with that and see how it transforms. So the tensor T operating on alpha U plus beta V, for it to be linear, it means that it should give you alpha TU plus beta TV for us to have a linear transformation. So now let's see what happens. If you look at 1, what they are asking us to prove is that this transformation Oh, sorry. Let me go back to my black pen. Is equal to A dot, anywhere you see V, just put in that weighted sum. E1. So they are asking us to show that this transformation I just wrote on the whiteboard is a linear transformation. That's what we are supposed to prove. Okay, and for you to recognize a linear transformation, I've written it first of all. Now let's work on the right-hand side, because that is actually what we want to prove to show that is a linear transformation. So the first thing that you see is that this is a scalar product. And that scalar product can operate on each of these vectors. This is a vector. This is a vector, because the scalar multiple of a vector is a vector. This is a vector, and this is a vector. First of all, you must recognize that this is not something you have to guess. You must recognize it to be sure that the operation you are carried out is actually valid. So for example, this is a dot product. I can say, oh, this dot that I put here is valid because a vector, you can do a dot product of a vector and a vector. So that operation is valid. So if I open up that bracket, because it's a scalar product, this gives me alpha u plus a dot beta v, and everything E1. Now, if I further open up, the E1 is going to everything in each of those brackets. Now, let me ask us a question. This, in this small bracket, the result, will it be a scalar, a vector, or a tensor? Look at what I underlined here. And I want your responses in the chat room. A dot alpha u, when I perform that operation, my result, will it be a scalar, will it be a vector, or will it be a tensor? Bolaji says scalar, waiting for more. Mubarak, scalar. Fantastic. So I just wanted to be confident that everybody can recognize the kind of products you should get from some operations. Scalar, Kyode, I can see you, I can see everybody. Very good. So it means that this will give me, is going to be the same as saying alpha is a scalar. So I can bring it out. It won't change anything. So I can write this as alpha a dot u E1. And the second one also, I can write as beta a dot v E1. And looking at that, you can see that u E1, you can see from what we have there, that the tensor that we had, look at the question, the tensor that we had over here operating on the vector was actually supposed to be a dot v E1. So it means that what I have here is the same as writing alpha tu plus, let me clean this, plus beta tv. So if you look at the transformation of number one, tv is a dot v E1. So it means that my alpha a dot u E1 is the same as say alpha tu, and my beta a dot v E1 is the same as say beta tv. And if you look at the linear transformation I wrote here, first of all, you can see that that transformation satisfies it. So it means that indeed 1 is a tensor transformation. So all you just need to do is to work it out step by step and see that the results that you actually get shows a linear transformation, just like I have done. Any questions? And if you want to unmute yourself, just raise your hands and I'll ask the admin to allow you unmute. Any questions? Okay. Okay. I would like you to, the last step, okay, what you need from the last step, Bolaji, is to look at the question. The question says that show that TV, which is equal to A dot VE1, is a linear transformation. So if you look at this, you will see here we got A dot UE1. Do a comparison of the question with that. So that means that A dot UE1 can also be written as TU. I hope you can see that. And the second part after the addition sign, A dot VE1 is TV. And that is why this step becomes the last step. I hope you can see that from the question itself. The question itself gives us that transformation on the vector V. Okay, let's go to the second one. The second one says that we should show that TV is A cross V, and that is a linear transformation. And if you look at this very closely, you might be wondering, how does a tensor come in here? But you know that this can also be written as A cross V. And when you have that A cross, that's what we call a vector cross. And a vector cross have been proved already in chapter 2, have been proved to us that it is actually a tensor transformation. But another way that you can do this proof is to write it in index notation. And we can now show the proof very clearly. Remember that instead of V, we are going to be using alpha U plus beta V to show the transformation. So it means that anywhere you see V, you replace it with alpha U plus beta V. And you will also remember that for you to write the vector cross, as shown to you in chapter 2 in index notation, A cross in index notation is written as alternating symbol IJK, AJ, dyad of EI, EK. One of the things you will see also here is the pattern for writing the vector cross in index notation. Look at the alternating symbol, IJK. You will see that the subscript, the index on A, is the middle index on your alternating symbol, while the other two indices is what makes up your dyad. So you see J is in the middle here. That will be the index for your A, which is your vector. Then the other two indices will make up your dyad. So that is a pattern you need to recognize when you are writing the vector cross, as shown to you right now. So now let us write, instead of having A, let us write alpha U plus beta V I'm supposed to write A cross alpha U plus beta V. So I'm supposed to allow that vector cross operate on this. Oh, sorry, my apologies. So what this is doing, what we can see here is that we are not looking at the V, we are actually looking at the A cross, because that is our tensor. Please let me go back. I think I might have caused a little bit of confusion. Please let me go back. Remember that in the first question, we had TV. We wanted to show that the transformation will be this. That's what we wanted to prove. Okay. So anywhere that we saw V, we put in alpha U plus beta V. Okay. But now what we want to look at is this vector cross. So instead of us having A cross, we are now going to replace it with this weighted sum. And we are going to see whether when it operates on a vector, it's going to give a linear transformation. So if we are going to write that cross, so let me just correct that error. So we are not replacing alpha U plus beta V anywhere we see V. We are actually looking at the tensor itself, which is T. We want to see if actually that will give us a linear transformation. So let's do that cross. So A cross gives us this. So what it means is that alpha U plus beta V cross is equal to EIJK. Anywhere you see your A, just replace it with alpha U plus beta V J EIEK. So that's what you have. Now, let's look at what we have here. What you have there is the same as writing, that's alpha U plus beta Vj is your J component of your vector. So what it means that would be EU alpha Uj plus beta Vj. So you see this J outside the bracket means that we are looking at the J component of U and the J component of V. And this is how we are going to write that. So if we put that back into our vector cross, it now becomes EIJK alpha Uj plus beta Vj EIEK. And that will be the same as saying EIJK alpha Uj EIEK plus beta Vj EIEK. Without this operating on a vector, you will see that already we have something like a weighted sum that looks like a linear transformation. So this vector cross can operate on any vector. And when it operates on any vector, you just include the vectors at the back. And you will see that this weighted sum actually looks like a linear transformation. This weighted sum looks like a linear transformation. So you will see that TV, which is equal to A cross V, is actually a tensor transformation. Any questions on any step that I just did now? So the first thing is to actually show that the alpha U plus beta V cross is actually a tensor transformation. And what we have done is to show you step by step. So when this tensor operates on any vector, you will see that what you will get is actually the weighted sum being separated in a linear way, like it should be for a linear transformation. Okay, can you, Mojira, maybe you want to unmute which of the steps? Let me just label the steps for you. This is step 1. This is step 2. This is step 3. And this is step 4. So where did you get confused? 1, 2, 3, 4, so that I will know what I'm focusing on. Okay, step 1. Okay, for step 1, you will actually need to get this that I'm putting in rectangle now is in the notes. So if you have not read the vector cross in the notes, that might be a challenge. But for the purpose of this class, what I just need you to do is to recognize the pattern of writing the vector cross in index notation. And you can see that pattern as I put it in the rectangular brackets. Is it clear? Is that clear? Is that pattern clear to you? Because that is the first step for me to now replace A with alpha U and beta V. Okay, once that is clear, anywhere you see A in that vector cross, put your weighted sum of 2 vectors. So you will see in step 1, all that I did is that anywhere I see A, just put in that. Is that clear? Is step 1 clear now? Okay. Now, after that step, what is step 2 doing? In step 2, I did not write out everything. I just took out, if you are looking at what I'm doing right now, I just took out this portion to further elaborate on how to write that. And step 2 is just saying we are only looking at the J component because that is a scalar. The J component of what is in that bracket. Remember, what is in that bracket is a vector. So I wrote it out for you. So alpha U plus beta V into bracket J. I have to write the J component of each of those vectors and add it. Is step 2 clear now? Step 3 is just putting in back what I did in step 2 back into the vector cross. So I put it back into the vector cross. Now, if you look at that clearly, you will see that what we have there is the addition of two scalars with the alternating symbol. So look at step 3 very well. So let me move to step 5. Maybe I should do that. Let me move to step 5. So step 5, the end product is that alpha is a scalar. Alpha is a scalar. So I can write this as alpha EIJK UJ EIEK. On the other end, let me just put this in brackets so you know that that is one part. On the other end here, I will have beta EIJK VJ EIEK. If you look at this very well and look at the index notation for your vector cross, you will see that this is the same as saying alpha U cross plus beta V cross. Yes, because what is in the bracket is their scalars. Bolaji, we open the brackets in step 3 to 4 without any usual regard for the diode operations. The diode operations do not change. The diode operation was EIEK from start. If you look at step 1, all that I just did is that the positive sign is on the scalars, and you have that diode operating on your alternating symbol and what is in that bracket. So the diode is going to operate on each of those, each of the scalars in the bracket. Alpha UJ is a scalar, beta VJ is a scalar. And you needed to recognize that because you see I didn't put any bar there. And it had an index. Okay? And it had an index. So, but you would see that there's a way, if you look at how we write the vector cross, look at the vector cross, A cross. Can you see what we have there? Now look at step 5. Can you see that what we have that we are summing together on both ends are vector crosses? The first one, alpha U cross. The second one, beta V cross. So Mojirade, are the steps clear now? Bolaji, Akyode. So I didn't do anything unusual because what we have in the brackets are scalars, okay? They are not vectors. Okay, good. Now, there are some other people in the class, and I'm just hoping that they are following. Damilola, I've heard from Fisayo, Godwin, Kenneth, Lawrence. Okay, I've heard from Mubarak, Mohammed. I hope we are following. It's very, very important for me to hear from you also if you have any questions. The only reason why you want to ask me questions is that you have not gone through the materials. But if you have gone through the materials, please feel free to ask me questions. So you will see that what we now have here is like a weighted sum. We started with alpha U plus beta V cross, and we ended up with alpha U cross plus beta V cross, which is a linear transformation. And once that operates on any vector, that's what it's going to look like. So if this operates on, maybe for example, a vector C, so what you have is alpha U cross C plus beta V cross C, which is a linear transformation. Okay, I hope that was really explicit. Hopefully, and not hopefully, definitely you get the recording. So if you don't even grab everything now, you could just listen to my voice over and over again and until it is clear. Now let's go to 2.5. Let's go to 2.5. Can I go on? Can I move on? Okay, good. Now 2.5, which is another level. You remember that we said we are going from simple to more challenging. So 2.5. Okay, Mohammed, I see you. Of course, you get the recording, so I'm sure that will be sorted. What tensor transforms the basis vectors as follows? So we are looking for what tensor T transforms TE1 to be equal to E1 plus 2E2 plus 3E3 and transforms E2 to be minus 5E1 plus 4E3 and transforms E3 to be 3E1 minus E2 minus E3. So when they're asking us what tensor does this kind of transformation, so we are looking for that tensor T. Now, if you write your tensor T in its full form, remember that normally if you have your T, if you want to write it in index notation, you can write it as Tij, Ei, diad Ej, where our I and J goes from 1 to 3. So in full form, this is what it looks like. E1, E2, E3, diad of your T11, C12, C13, T21, T22, T23, T31, T32, T33, E1, E2, E3. So this is writing it fully, you know, expanding it fully. And this is one of the benefits of vector and tensor algebra. You can write in short form. You can imagine if we do not understand the language of tensors, we have to keep writing this thing fully in everything that we are doing. And that will be a little bit laborious for us. But instead, you can write it in this short form, and it means exactly what I've just written. This is another reason why some people say, oh, tensor algebra is just like you doing vector algebra. No. Even though what you can see here is a 3x3 matrix, but what makes this a tensor is actually these dyads. Without these dyads here, you don't have a tensor. What you just have in this square bracket, this 3x3 matrix is just the scalar component of that tensor. So this is what we are looking for. We are looking for what is T11, what is T12, what is T13, T21, T22, T23, T31, T32, T33. That is what the question is asking. The question is asking you to find what T is. And T such that when it operates on the basis vector, it gives you what we have on the right-hand side. So that is the question. So how do we progress? How do we progress? Remember that we know a tensor by the way it operates on a vector. We know a tensor by the way it operates on a vector. So for example, if what I had was TV, okay, if what I had was TV, if I'm going to write this in index notation, okay, if I'm going to write this in index notation, what I will have will be Cij, Ei, Ej, and so that I will not have any clash with my index notation. Remember, there are rules for index notation. An index cannot be repeated more than 2 times. So I'm going to use another index for my V. My V can now be V alpha, E alpha. So if I write it this way, it means that my TV, what is going to give me is Tij, which is a scalar, the scalar component of that tensor, V alpha, which is a scalar component of that vector. Then I put all the bases out. Please follow this step by step, even though this was not written out this way. But you will need to understand this for you to actually capture what is going on in that 2.5a. So are we clear up to this point? Are we clear up to this point? In my writing TV, T operating on V? Hello, everybody. Okay, what are you trying to understand? I wrote T, Mujiradi, I wrote T in its index notation. I wrote V in its index notation. T is Tijei, that product Ej. That's T. If I'm going to write it fully in its index notation, that's what it is. If I'm going to write V bar fully in index notation, is V alpha, E alpha. So all I just did was bring all the scalars together. Tij, V alpha, they are scalars. I brought them together. Then I brought the basis vector together. So you see, I have the dyad Ei, Ej, then I have E alpha. That's all I've done so far. Is it clear? I've not done anything extra. All I'm just doing is I'm writing TV in index notation. That's all. That's all I've done. And there's something I want to get. Okay. Okay, great. So now permit me to take off what I have on the board so that we can continue. So TV in index notation so far now, what I've written is Tij, V alpha, Ei, Ej, E alpha. And of course, when a diode operates on a vector, this is what you get. Cij. I've not started the proof yet. I'm just trying to write a form of TV so I can see what we have. This will be Ei, and this will be Ej dot E alpha. I hope you can recognize why that happens. That is clear. Remember, your A diode B operating on V will give you A into B dot V. So you have to keep that right. You have to keep remembering those operations for you to know what happens. So this becomes Tij V alpha Ei dot product of your autonomous bases gives you the chronicle delta. Gives you the chronicle delta. And you know that your chronicle delta can be used as the substitution symbol. So I'm going to use the substitution on the V alpha. The alpha on the chronicle delta, you see alpha on V. So I'm going to use that substitution symbol, and my V alpha now becomes Vj, and the chronicle delta is removed completely. So this is what we have. Is it clear up to that point? And that is why if you are looking at your notes, I want you to just take a look at 2.5a. You will see where it's writing applying TV is equal to Tij, Vj, Ei. We are for V equal to E1 as, so that's where we are. What I just showed you now is how come TV is equal to Tij, Vj, Ei. That's the part of the note I just explained. Can we see that in 2.5? In the note, it just assumed that you should recognize that TV is written in that form, but I needed to elaborate so you could see how we arrived at that. Okay, so now let's continue now. But in our own case now, remember that for our own case, our V, what we are looking at is TE1. What we are looking at is TE1. So for a case where our E1 now, we are going to substitute, wherever we see we have V, we are going to substitute it with E1. Wherever we have E, we are going to substitute with E1. So in our own case, we are saying our V is E1. But we all know, everybody here knows that when we are writing V in its full form, is V1 E1 plus V2 E2 plus V3 E3. I hope you remember that. That's writing V in full form. So for us to now say our V is E1, what does that mean? What it means is that our V1 will be equal to 1. Our V2 is 0. And our V3 is 0. That is the only way that we can say that our V is equal to E1. That is the only way we can say our V is equal to E1. So if you are looking, if you just put this by the side, write this somewhere. So when you say your V is equal to E2, what it means is that if you say your V is equal to E2, what it means is that your V1 is equal to 0. Oh, sorry, V1 is 1. Thank you. Thank you for spotting that. V1 is 1. What it means, when V is equal to E2, it means that your V1 is 0, your V2 is 1, and your V3 is 0. And for the case where your V is equal to E3, what it means is that your V1 is 0, your V2 is 0, your V3 is 1. And that is how, if you are looking at the solution, that is how you can understand how you are substituting 1 and 0 into what we have, what we have over there. So write this in one place. What I want to do now is to expand this fully, where I and J goes from 1 to 3. So what we are doing with example 2.5, there are so many skills we are bringing in. Instead of me just answering the question or solving the problem the way it is in the notes, I am bringing in, different knowledge steps that will be useful for you in other examples, which maybe I could have just assumed that you should know, but I don't want to make that assumption so that you can see it and it can be clear to you. So for us to actually write out what is in the brackets that we can see here, I need to write out the TIJVJ E1 fully. So what I want to write right now is TIJVJ E1. That's what I want to write. I want to write that out before I now apply V is equal to E1. I want to write that out fully before I write V is equal to E1. Oh, I'm too fast. Akiode, I really, really apologize. I really apologize. You would have slowed me down ahead of time. Okay, so I'm going to pause a bit. I'm going to pause right now. Allow you all to look at this, then wait for questions. So let me give you maybe a 2-minute break just to look at what I'm doing. Let me know when I can go ahead, and let me know if you have any questions. So I'm just waiting for you to talk to me. Questions, or I should go on? And I need you to be looking at what is on the whiteboard and what you can see in the solution. So that's where you will understand where we are. I'm not just solving this out of context. You need to be looking at your notes so that you will know where we are and you will be able to understand where we are in the solution. Okay, Mubarak says I should go ahead. Akiode, I hope I've slowed down enough. Okay, so let me take this off. Everybody, do you know, can you see where we are on 2.5 in your notes? Are you on your notes right now? Because that's important. Because I'm looking at the notes to be able to explain to you on the board. Just confirm to me that your notes are open. I mean the chapter 2 that we are solving. Okay? It's only Mojirade that says our note is opened. If yours is not opened, you might not know what is going on. Okay, there are a couple of people, so let me go on. So now, what you can see as next step is our TIJ VJ EI. So if we write that out fully, what you will have is T11. Remember that your J is a dummy index, a repeated index. So with that, you will see what we are going to write. So T11 V1 plus T12 V2 plus T13 V3 E1. So what you see on your I is what we go on your E, plus T21 V1 plus T22 V2 plus T23 V3 E2. Because the index I is on the first index on T and also what is on your basis vector, plus T31 V1 plus T32 V2 plus T33 V3 E3. So our first case that we are looking at is when your V is equal to E1. And we already established that in this case, V1 will be 1, V2 is 0, and V3 is 0. So you will see that that will give us the transformation for TE1. Now, for the case where our V is now E2, V1 will be 0, V2 is 1, V3 is 0. And for the case where V is E3, that can only happen when V1 is 0, V2 is 0, and V3 is 1. So we are going to substitute all this. So for the case where we have TE1, your V1 there is going to be 1, your V2 is going to be 0, your V3 is equal to 0. So what we have in that first case is going to be T11 E1. And for the second case, if we are looking at the notes, for the second case, we'll see, just hold on a minute. For the second case, you will see that V1 is 0, V2 is 1, and V3 is 0. So what we have there will be, let me remove the brackets, plus T22 E2. And for the third case, what you will have there is our T33 E3. So I'll pause a minute so it won't be as if I am too fast. I just want to cross-check with what is in the notes to be sure. There's an error in the note, so you might have noticed. You will see that the first thing that I've written there is for just give me a minute. Okay. And this is supposed to be equal to, and that's where the error is in the notes. This is supposed to be equal to E1 plus 2E2 plus 3E3. So if you look at the note, it was the last one that was written first. Yeah, the note is different because there was an error. If you look at it, you will see that it was what was written for TE3 that was written for the first one. So that was an error. If you look at the final answer, you will see that I've corrected that error. Look at what was written for TE3 in the notes. Actually, check the TE3 in the notes. You will see that it's the same thing written for TE1. So that was a typo error. Akionde, can you see it? And everybody. Mojirade, that's the question. If you look at the question, you will see what tensor transforms the basis vector as follows. TE1 is E1 plus 2E2 plus 3E3. That's the first one. So the E1 plus 2E2 plus TE3 is what the question is asking. And by equating it, what we want to get, remember that what we are looking for is the tensor. Everybody, we need to always remember what the question is. We are looking for this. This is what we are looking for. So we are looking for what is T11, what is T12, what is T13, what is T21. So it is by equating what we've done now with, remember, we want to see what tensor transforms to E1 plus 2E2 plus 3E3. So when we equate it, we'll now be able to see that T11 is 1, T22 is 2, and T33 is 3. So we've gotten those 3. Mojira, where do we get 2 and 3? Actually, I don't get your question. But Mojirade, do you understand what we just did now? We are equating what we wrote out fully with what the question is asking us for. We are looking for what are the values of T11, T22, T33. So from what we have done, by equating it to the question we're asked, we can now get what the value of T11 is. Okay. Akiode, please, admin, let Akiode unmute.
Hello, ma.
Yes, go ahead.
See, by equating all those values that we were able to get 2 and 3.
Yes, but let me just hold on so that you can talk. Everybody, let me take this off. There is something that you might not really see that I want you to see. Remember that what we expanded was T-I-J, V-J, E-I. Do we remember that?
Yes, ma.
Do you remember that that's what we expanded? Do you remember that the first question that we have is T-E-1? We
Yes,
want
ma.
to see what vector transforms this into this.
2E2 plus 3.
So the idea is that when you expand what is on this side and you equate it to this, you will get some of the components of T. So when you expand this side, you will get all the components of T. And remember that we have Tijvj that we expanded. And when we expanded it, we got the portion where your T, we actually have your 3x3 matrix. But in doing those competitions, some of them will fall out. And you will get what the result is. So I want you to go back to your notes, Akiode, while you're muted. Go back to your notes and see what the expansion for TE1 is.
Okay, ma.
Can you see it?
Yes,
Can
yes,
you
ma.
see that it's the same as the expansion we did for TIJ, VJEI?
Okay. I can get it,
And
ma.
everybody that is not unmuted, please, that's why I said open your notes. You have to be looking at the notes and looking at what I'm doing. Because what I'm just doing here is to explain each step. So any missing information, you can get it in the tutorials. So if you look at the expansion of TE1 is equal to, you will see that that's the expansion that we did for TIJ, VJEI. Now, why did we use that expansion? Go to the previous step. You will see that TV is equal to TIJ, VJEI. Then for V equal to E1, because if V is equal to E1, what happens is that we are going to have two basis vectors, and what you have will be TE1. So for V equal to E1, that is the expansion that we have. And if you put all the these substitutions that we've done now, you will now see that your V, your T11 will be equal to 1. Your T22 will be equal to 2. And your T33 will be equal to 3. So everybody check your notes, look at the expansion. If you look at the expansion, you will see that V1 is 1, V2 is 0, V3 is 0 for the case where you have your E1 in front. Okay? So for your V equal to E1, that's what will happen. I hope we are all following. I want to be seeing responses in the chat room. If you now go to the second one where we have E2, you will see, let me see what happened here. Oh, I'm seeing some errors here. I'm seeing some errors in the notes. Just hold on. Let me look at my own notes. Give me a minute. I can see what Akyode is pointing to now. One minute, please. I've done this. I've written it out here. So let me just compare what I wrote out here with what is in the notes. Oh, okay. I've seen the error. Everybody, sorry. I've seen the error. My apologies. So let's do that expansion. I've seen it. What I substituted in my expansion was not correct. So let's, Akyode, you can mute now. I've seen where the confusion is coming from. Okay, so let's expand back our T, I, J, V, J, E, I. So let's start from there because that was clear to everyone. So that's T11, V1 plus T12, V2 plus T13, V3, E1 plus T21, V1 plus T22, V2 plus T23, V3. E2 plus T31 V1 plus T32 V2 plus T33 V3 E3. All right, so the error came from the fact that, remember that for the first one, it is V is equal to E1. And for that case, for V equal to E1, all our V1s will be 1. All our V2s will be 0. And all our V3s will be 0. The first case we are looking at is TE1. We've not moved to the second one. What I did was that I did E2 and I did E3, which was not correct. So for this expansion I've done now, we are going to apply it for this case only for now. So everywhere that you see V1, replace it with 1. Everywhere that you see V2, replace with 0. And everywhere you see V3, replace with 0. Is it clear to everybody now? Akyode, well clear. You see that what I wrote initially is different from the expansion in the notes. So once you do that, you will see that that TE1 case will now give us T11E1 plus T21E2 plus T31E3. And that will be equal to, the only error that was made in the notes is that it was supposed to be equal to E1 plus 2E2 plus 3E3. That's the first case. So when you equate it, you will see, looking at comparing both sides, you will get your T11 to be equal to 1, your T21 to be equal to 2, and your T31 to be equal to 3. Now, it is when you now go to the case of TE2, which is the second question, that you will now say V1 is equal to 0, V2 is equal to 1, V3 is equal to 0. So everything you see in this expansion, you will replace all the V1s with 0, replace all the V2s with 1, replace all the V3s with 0, and you will now get T12 E1 plus T22 E2 plus T32 E3 equal to the second question that you have there, minus 5E1 plus 4E3. So what it means here is that your E1 is minus 5, your T12 is minus 5, your T22 is 0, and T32 is 4. Then you now do the next step again for your V equal to E3. So in that case, V1 is 0, V2 is 0, V3 is 1. Then we replace every V1s in the expansion with 0, every V2 in the expansion with 0, and all the V3s with 1, and equate it to the last question. And you will now get, so you will get all your values for T11, T12, T13, T21, T22, and T23, T31, T32, and T33. And you put that in that matrix, and that will be the tensor that you are looking for. Have I clarified where the confusion is, at least up to this point? We are going to end today at this point so that you can go review what we just did. We'll still start with, we'll continue with the from 2.5, but the recording of today's lecture, you will get it as soon as possible. We are going to have another session on Wednesday. So on Wednesday, the chosen questions that I have is that from 2.5, we do 2.6, we'll do 2.10, 2.18, and we'll see how far we go. Remember that I already did some of these questions with the previous, with the PG 2021 video. So what I'm trying to do is I don't want to repeat the same thing so that we can cover as many questions as possible. So any question that was already captured in that 2021 video, I'm not going to do again. So I can deal with new questions. So by the time you are looking at the two videos, at least you can capture as many questions as possible. So I'm going to end today's lecture at this point. I'm hoping that the tutorial was useful, at least to be able to elaborate on the few worked examples we looked at. On Wednesday, I'm hoping that we can move faster and deal with ones. Oh, Akiode, oh, yes, okay. So Bolaji, please explain to him. And I'm even hoping when you get the recording and listen to it again, I'm sure you'll be clear, okay? So thank you everybody for coming in today. Please, let's review what we did today.